Hi, and welcome to this lesson on surface area. By now you have all the tools you need for calculating the surface area of many objects or structures, any that are made up of some kind of right prism or cylinder. The surface area of some structures can be found easily from the net of the structure. For others, it will make more sense to work out the total surface area using the views of the structure. Either way, you need to know the number of each type of surface and use the area formulae that you have worked out for shapes like rectangles, triangles, and hexagons. Now, are you ready for a new challenge? In this lesson, we will investigate what happens to the surface area of a rectangular prism if we make some of the sides longer or if we make all the sides longer. By the end of this lesson, you should be able to investigate how an increase in the dimensions of a prism changes the total surface area of the prism, and estimate and calculate the total surface area of an enlarged rectangular prism. Have your matchboxes ready so that you can try all the exercises in this lesson. That way you will make your own discoveries and not rely on what we have discovered. It is always useful to look at a simple two-dimensional shape first. Here is the rectangle we used in an earlier lesson. We found its area quite easily by using length times breadth or base times height. It was 3 times 6, which comes to 18 square units. Now, if I double the length and the breadth of this rectangle, how will this affect the area of the new shape I have made? How much bigger do you expect the area will be? Is the area double of 18 square units? If we are right, that should come to 36 square units. Well, let's work it out. The breadth becomes 6 units. And the length becomes 12 units. And 6 times 12 gives us 72 square units. The new shape is actually 4 times bigger than the original shape. Look again. This does make sense because doubling this side and this side allows us to fit our first shape into these parts of the new shape 4 times. Does this happen with every shape that has all its sides doubled? You need to test this idea out with the other shapes we have investigated in this series. What happens to the area if you double all the dimensions of a parallelogram, or a triangle, or a kite, or a trapezium? Can you draw conclusions about what effect doubling of dimensions has on the total surface area of these shapes? I will leave this investigation to you to do as your task. In the next lesson, we will also have a look at what happens to the area of a circle if you increase its radius. Now we need to test the same idea with a three-dimensional structure. We will use a right rectangular prism. This prism has a length of 3 units, a breadth of 1 unit and a height of 2 units. What is the total surface area of this prism? Let's take 1 square as a square unit. Then we can just count the squares. There are 3 here on top and another 3 underneath. 6 on each of these sides and 2 on either end. That makes 12 plus 6 plus 4 square units, which comes to 22 square units. If we double all the dimensions of the structure, what do you expect to find about the new total surface area? Will it be doubled or more? How much more? This length becomes 6, this length becomes 4, and this length here becomes 2 units. Do you agree? We have doubled each length of the original prism. Doubling all the lengths makes the structure a whole lot bigger. Do you think the surface area has been doubled, or perhaps enlarged 4 times, or 8 times more? The surest way of knowing is to count the blocks. Remember that each one is a square unit. We get 12 on the top and the bottom, 24 here, and 8 on each end. That's 24 and 48 and 16, which comes to 88 square units. 88 is 4 times as much as 22. So doubling all the dimensions of the original structure creates a surface area that is 4 times more than the surface area of the original structure. What is interesting here is that areas are measured in square units. The total surface area is a squared measurement. Squaring lengths that are doubled results in an area 4 times bigger. So if the length, the breadth and the height are all doubled, it is not surprising that the area is 4 times bigger. Let's see what we can find out about surface area when only one of the dimensions of a structure is increased. You can use your matchboxes for this activity. Have a look at this matchbox. In a previous lesson, we measured all its sides and we found that this side was 5,2 centimeters. This side here was 3,7 centimeters and the height here was 1,6 centimeters. To find the surface area of the matchbox, we found the area of each of its surfaces. These two surfaces will be 5,2 centimeters times 3,7 centimeters each. Remember that the answer you will get will be in square centimeters. These two will be 3,7 centimeters times 1,6 centimeters, and these two will be 1,6 centimeters times 5,2 centimeters. When we add all these surfaces together, we get 66,96 square centimeters. This is almost 67 square centimeters. Now here's my question to you. We have made a new structure by gluing 3 matchboxes together like this. Estimate what you think the surface area of this new structure is. Take a guess using what you have seen in this lesson already. Did you guess that we should take 67 and multiply by 3? Have we made our surface area 3 times bigger? Although the shape is 3 times bigger, we have to think about this. We need to base our estimate on what we know about the different types of surface. We have only 2 of these small surfaces, which are 1,6 centimeters times 3,7 centimeters. That came to 12 centimeters squared if we round it off. We have 1, 2, 3, 4, 5, 6 of these surfaces. That is 3 times more than we had before. We had about 40 square centimeters, so that's about 3 times 40, which is 120. And then these surfaces, 3 at the top and 3 at the bottom. That's also 6, 3 times more than on one box. We had about 17 centimeters squared. So 3 times 17 is 51. Our estimate is about 12 plus about 120 plus about 51, which is about 183 square centimeters. I will leave it to you to find out how close to the exact measurement we were. What is important here is this. When we made the length 3 times longer, we kept the breadth and the height the same. We cannot assume that the new surface area is 3 times bigger. We need to consider which surfaces have increased in size. These side surfaces are 3 times longer, these top and bottom surfaces are 3 times longer, but these surfaces have stayed the same. Let's recap what we have discovered in this lesson. Firstly, if you double all the dimensions of a right rectangular prism, the surface area of the new structure will be 4 times bigger. We only tested this on one prism. That's not enough to make a rule like this. You need to check if this generalization is true. In class, you could each make a different sized right rectangular prism, find its surface area, then double its dimensions and find the new surface area. We also saw that if you increase only one dimension of a prism, this increases the surface area of some of the surfaces, but not all of them. We need to consider each surface separately. I've already suggested that you investigate what happens with other two-dimensional shapes when you increase their dimensions. Now here's another task that continues with this investigation. Use your matchboxes to work out A. The surface area of a tower of 3 matchboxes made like this. Compare your answer with the one we found in the lesson for a train of 3 matchboxes. Explain why this structure has a smaller surface area. Well, we seem to have covered all you need to know about doubling sides of right rectangular prisms. So in our next lesson, we look at the cylinder and doubling its sides.